Hi, my name is Harrison Butker, and today I will be discussing Lab 4 oscillations. In this lab, I was asked to examine the motion of a mass oscillating on a spring along both the x and y coordinates. The purpose of this lab was to understand that from a fundamental principle, I could predict the future motion of the mass and also that the energy principle remains true for this motion. My results show that the energy principle proves to be true for this motion. Here is what the oscillating mass looks like along with the various tracker points. To predict future motion, I first started from a fundamental principle with Newton's second law. V final is equal to V initial plus F net divided by the mass times delta T. I also concluded from Newton's second law that the final position is equal to the initial position plus the velocity times delta T. To predict the various positions and velocities of the mass, I needed to find F net. The two main forces acting on the mass are the spring and gravitational forces. The force vector of gravity is equal to negative m times g times a unit vector in the positive y direction, and the force vector of the spring is equal to the spring stiffness times the difference in spring lengths times L hat. After adding these two forces, I inserted F net to Newton's second law and successfully predicted the future motion of the mass. In order to see if I correctly predicted the motion, I first applied the equations into the Python code and then ran it. As you can see, the red ball is the actual ball that I looked at in the video, and the blue ball is the predicted motion, and it follows it almost perfectly. Next, in order to test the validity of the energy principle of this motion, I started from a fundamental principle, specifically the energy principle. The energy principle states that the change in energy on the system is equal to the total amount of work applied to this system. Since our system is a spring plus the mass plus the earth, there is no work being done on the system, so the change in energy is equal to zero. Since work in this case is equal to the change in kinetic energy of the mass plus the change in potential energy of the spring plus the change in potential energy of gravity, I set the sum of these quantities equal to zero. Now I can plug in the equations for these quantities. Kinetic energy is equal to 1/2 mv squared. Spring potential energy is equal to 1/2 k sub s times s squared, with s being equal to the length of the spring at that instance L minus the relaxed length of the spring L naught. And the potential energy of gravity is equal to mg times the height. In order to see if the energy principle is satisfied, I need to show that delta k plus delta ug plus delta us is equal to 0. To find the change in these quantities, I made a loop within the Python code that subtracted initial values from final values. Here's my Python code, and as you can see, I just translated the equations to make sense for the Python code, and then I plugged in delta k, delta ug, and delta us being just the final values minus the initial values. I decided to plot the summation of these changes of energies, and as you can see, the yellow graph represents the total change in energy, which is along the x-axis, which means it's equal to 0. When you add the red graph, which is the change in potential energy of gravity, plus the green graph, which is the change in potential energy of the spring, plus the blue graph, which is the change in kinetic energy of the mass, then you get the yellow graph. The second part of the what does it mean question asks us to estimate the oscillation periods of both the x and y data points. I first looked at the initial x and y positions of the mass and then tried to find the time at which these values occurred again. As you can see, at t equals 1.52, the x and y values are the closest to their initial values. Therefore, the estimations of the period of oscillations for the x and y positions are therefore the same. Thank you.